All right, everyone, if we could please take our seats. We'd like to get started. Welcome, welcome. Hello. I'll just give the intro when All right, everyone, if we could all please quickly try to take a seat. So we have a lot of presentations to get through. All right. Welcome, everyone. Good morning. Good morning. Hello, hello. My name is Dr. Rita Blake. I'm the Manager of Education here at the California Nanosystems Institute at UCLA. So for those of you visiting us today for the very first time, welcome to CNSI. Sure. Why not? I like applause. So just really quickly to let you know kind of where you are if you've never been here. So the CNSI is a very different sort of place here on campus. So unlike a lot of departments that are academic specifically, CNSI is not exactly an academic department. We are a research institute that tries to leverage public and private investment to try to promote interdisciplinary research and innovation based around nanoscience and nanotechnology. And so I think about 8 or so years ago now, we decided to start summer programs for students that were based off of the experiments and workshops that we've been developing for many, many years, even before then, for high school students. Because a lot of people maybe have heard of the word nanoscience, but very few people know what it means even, let alone like what are the actual things that are happening with nanoscience in the world today. So this is one of a few programs that we have, and it's one of my favorites personally for some of the reasons that you will see as your students are going to be giving presentations today. Before we get started, there's a few people that I need to introduce and thank. Again, my name is Rita, in case you're wondering who's been with your students for the last few weeks. Also, I have to thank Dr. Elaine Morita, who is our program coordinator, because without her, things would not run or function for this education program. She has been a vital resource into getting everything organized and created for this program. So I don't know if Elaine's in here, but wherever she is at this very second, let's please give her a big thank you. And also, before we continue, I wanted to introduce the instructor for this course, Professor Sarah Tolbert, who is in the departments of chemistry and biochemistry, as well as the Department of Material Science, and is one of the many researchers who are members of CNSI. So, Sarah, would you like to say a few words about the program?
Are you going to introduce the rest of the people?
Sure.
Let me say something between that and when people start talking.
Sounds good. Okay. And who your students have really been working with very, very closely throughout the whole week has been their instructors. So all of their instructors are graduate students here at UCLA pursuing their PhDs in the sciences and engineering. And they are all standing right here. So we have Omar Garcia, Yolanda Lee, Jesus Iniguez, Shailene Tanemoto, Zach Gavildis, and Kevin Cannon. So can we all thank them as well? They've been working exceedingly hard these last 2 weeks, and especially this last week, basically serving as PIs or principal investigators and sort of leading our research groups for this last week in their experiments. And we're all really excited to see what they've come up with. I mean, it's always extremely impressive what they can put together in a really, really short amount of time. That is very, very much crunch time for them. So I'm very excited to see what's going to happen. And there's also a lot of behind-the-scenes staff that I just want to give a quick acknowledgement to. Our event staff, IT staff, project staff, and also Mark, who I'll give a shout out to because he's helping with our live stream. So for those of you watching on the internet, hello. And thank you to Mark for always making that happen for us. And so I guess at this point, I might turn it over to Sarah to talk more about the details of the program and why we wanted to do it.
Okay, which of these mics are live? And this one you turned on?
All of these ones are live. And if
But
you
not
want to,
this one?
I think that one,
I don't like to stand behind the podium.
I don't know if it's on yet. I think that one over there should be live too.
Okay.
Yes. Okay, so you guys.
Excellent. I don't usually use a mic because I got a big voice, but I know that we're live streaming, so it really matters that you use a mic. So I want to start out by just saying thank you to all the students who participated in the program and all the parents who sent your students here. I have my very own high school kids, and I can tell you that figuring out what to do with them for the summer is not so easy. But what I want to do is just give you a little flavor for what your kids experienced during the last week, because there's a lot of summer programs out there for high school kids, and most of them are very what I call cookie cutter. This is what we're doing this week, and you will do it, and everybody will do the exact same thing. And we actually have other programs that are shorter that are a little more like that, in that we have defined set of experiments that everybody does, and we also get to see really high-tech facilities. But this program is different. And this program is different in that our goal is to give high school students a little more of a sense what real science is like. And so during the first week of this program, your students did a bunch of experiments that we defined, and we taught them a bunch of things. But during the second week, they were in control, and they came up with their own experiments. And this is the challenge that all real scientists face, which is, oh, here's an interesting system. What should I do to learn more about it? And that is the question that all of your students got to answer with the help of our amazing graduate student instructors. And today what you're going to see is presentations on their experiments. And so these are the experiments that they came up with. They're based on the original experiments that we did, and that's how science works. All experiments are based on what came before, and we build on knowledge, and we climb up that mountain of understanding. And that's what your students got to do. And so today what you're going to see is presentations on the experiments that they designed and the data that they were able to get and the new conclusions that they were able to draw. And this is really the process of doing science. And I think this is why this is Rita's favorite program, because this is the one where you see what it is really like to be a scientist and an engineer. And so I'm super happy that everybody gets to share those with you today. So just one thing. So first off, I need to apologize. I could only be here for the first 2 hours, and so anybody who goes at the very end, I am sorry, I will not be here to see your presentation. Now, to the parents, you are the outside observers. Your job, yes, you have a job, is to ask questions. Everybody has to ask some questions. And the fundamental rule is there is no stupid question. If you didn't understand what they were saying and you asked a clarifying question, well, then they deserve to explain it better to you. And if you exactly understood and have the most insightful question, then they deserve to figure out how to answer it. So please, everyone, ask questions, whether you know exactly what everybody's talking about or not. And I should say that for students, high school students, college students, graduate students, postgraduate students, when you stand up and give a science presentation, you did the experiments. You know what you did. But you never know what people will ask. And so the biggest fear at all ages is, what kind of a question am I going to get, and am I able to answer it? And the only way to overcome that fear is to just do it. Answer questions, figure out that even if you don't know the answer, you can figure out something to say. And so we need you all to help in that process, because if they give a presentation, everybody claps, and there's no questions, and they leave, they've missed one of the really great opportunities of giving a science presentation. So you know your jobs. I'll yell at you after each talk. And then when I have to leave, Rita will yell at you after each talk. So thank you very much, and we look forward to hearing all the presentations.
All right, so with all of that being said, let's just get right into it with our first group. So that would be turtle savers. Come on up.
So, by the way, these mics are very distance dependent. So even that much distance you can't hear. You really need to be right beside the mic. And that means if you're short like me, you have to turn it down or take it out of the clip. If you're tall, you got to tip it up. But they're really close distance dependent. So you've got to get super close. And many people haven't used a mic, or they just don't want to be near a mic. They're afraid to be near a mic. Just do it. Get close.
All right, good morning, everybody. We did our project on hydrophobic paper straws, and I'm Sangeeta.
I'm Adam.
I'm Natasha. I'm Vivi.
I'm Ian.
And this is our project. Oh, sorry.
So what inspired our project is that today there's been this huge public uproar about plastic straws hurting the turtles and destroying marine life. It's been this whole thing. So as an alternative, people have used paper straws, but those aren't much better either. They get really soggy over time, they break down, and they're just not really that good at all. And you often need like more than one paper straw for like one drink. And so, some vocabulary we'll need to know before we get into the bulk of our project. Thank you. Is surface wettability. That's the degree to which water will adhere to a surface. High wettability being when water adheres really well, and it would be really hydrophilic. And low wettability when water doesn't adhere to a surface very well, which is hydrophobic. And the last term we're going to need to know is nanoroughness, which are really small pillar structures on the nanoscale, which is 1/1000th of a meter, so times 10 to the -9, if you know anything about that. And they have really high surface area. And so our driving question for our research was, how can we create a hydrophobic paper straw that's both non-toxic and biodegradable? And our hypothesis is that if we can cap this titanium dioxide solution in oleic acid, then a nanorough and hydrophobic surface will be able to be created, and we can save the turtles.
So here's how we designed our experiment. First, we prepared captured oleic acid and titanium dioxide nanoparticle solution. And the way we do that is we first weighted the chemicals and we added acetic acid to the mortar. And as you can see in the top right picture, we're grinding it up for at least 25 minutes. And the reason we are grinding it up is because even though the TiO2 chemicals can seem to be really small, they're still at a micro scale, which is 10 to the -6. But then, as Ian said, nanoscale is 10 to the -9. So even though it seems like there's not of a big difference, there is, because the smaller the particle is, the more surface area there is. And they have the unique physical features that we can take advantage of. And then after that, we added oleic acid in order to cap the particles from getting too big and lose those features that we wanted to have. After that, we coated our straws with the TiO2 solution we made, like the picture shows. And after that, we allowed the straws to dry for at least 30 minutes. So here are just two GIFs that shows how the hydrophobicity works. So as you can see on the left, side, that's the regular paper straw, so we didn't do anything to it. And when you drop a water on it, you can clearly see that there's still some water that are attached to the straw, which makes it soggy after a while. But on the right side, you can see after we dropped a water droplet on it, it didn't stick to the straw at all. It dropped off, which makes it less soggy after a while.
Okay, so just to, again, verify hydrophobicity, so we dropped a water droplet onto our straw and measured the contact angle, and we measured it to be about 140 degrees. And basically, if the angle is greater than 90 and less than 150, it is considered hydrophobic. And then for our last step, we tested the properties of the straws by soaking them in water or weighing them. And basically, all of our testing is we tested durability by weighing them with pennies over here. So you can see in between the two tables, we laid our straw. And then we had like a little basket full of pennies that we dropped into. And then until the straw broke, that's how we measured durability. And then we also soaked them in water for different increments of time. And we tested the durability after soaking. And then we also tested them in different liquids. So we did Coca-Cola, and then boiling water, and then ice water. And then lastly, we stirred the paper straw and then our coated straw at a constant speed and to see which one would bend first.
So I'm going to take a closer look at the actual durability testing. So here we see that there is this straw, and we made some sort of basket contraption and placed pennies into it, and we have the weight of the pennies and the weight of the basket, and that pretty much tells us the amount of weight that this straw can handle, which in turn tells us the durability. So using this testing technique, we got this data, and we pretty much see that paper straws and coated straws here both have a very similar durability, from 10 minutes soaked in water to 30 minutes soaked in water. However, after 30 minutes, leading up to an hour, we see that the durability of the paper straw starts to decrease while the coated straw has a constant durability, which suggests that the coated straw can likely stay stronger for longer. Similarly, here we soaked our coated and our non-coated straws in Coca-Cola, boiling water, and cold water, and we see that the different durabilities are very similar, which is congruent to what we saw here, where at 10 minutes the durability is really similar. So it's positive because it means that our coated straws can also handle different liquids and liquids at different temperatures.
So the coated straws, they take more time to bend or deteriorate than the paper straws while it's being stirred. Because of the TiO2 and it's hydrophobic, the water, it does not absorb the paper straws. Yeah.
And so some trends that we found were that the TiO2 coated straws and the non-coated straws were pretty similar over short periods of time, but over long periods of time, the coated straws were overall stronger, but we could do more experiments to solidify those results. And some possible sources of error that could have affected our results could be that inconsistent straw lengths. So if you have a longer straw, it's going to hold less weight, and if it's a shorter straw, it's going to hold more weight. Because if you think about it like a crayon, if it's like your wax crayon and you keep breaking it in half, it gets harder to break in half over time, so a shorter straw would be more durable. And inconsistent straw overlay, so if it's unevenly placed, then it would hold less weight, but if it's evenly placed, then the weight distribution would have been better and it would hold more weight. And then the last thing that could have affected our results is that titanium dioxide by nature is really flaky. It's what's in white paint, so when it flakes, it makes micro cracks, and it takes away the nano features, which would make it more hydrophilic than hydrophobic, which would skew our results.
So for further research, we're going to have to find an alternative nanomaterial that's biodegradable, that sticks to the straw, and is non-toxic. And we also have to find, theoretically, all the chemicals that we put inside our straw are biodegradable, but we still have to check if the mixture of those chemicals is biodegradable itself. And around 5 to half an hour, the TiO2 straws have about the same durability of the paper straws. But afterwards, the coated straws are better than the paper straws. And while stirring, the TiO2 coated straws is like twice as better than the paper straw.
Thank you for listening. Do you have any questions?
Yes.
Great presentation. Just two questions. One, what is the, maybe I missed it, what's the specific property of TiO2 and the oleic acid that allows this? And the second question is, how did you measure that angle, 140 degrees?
Have you seen this diagram? You have this TiO2 nanoparticle right here, and you have this oleic acid molecule. The oleic acid molecule has this little group on the end of it with a hydrogen. It bonds to this oxygen electrostatically, so they're bound to each other. So it creates this like little shell around the nanoparticle, and then this end right here, it repels water because it's nonpolar.
And then, and then
Contact
to measure
angle.
the contact angle. So basically, we took this picture like flat on a surface, and then we used a protractor and lined it up right at that point. And then we used a protractor to measure the angle of the water and to see if it was super hydrophobic or hydrophilic or regularly hydrophobic. Any other questions? Yes.
Two questions. One is, did you look into any other material before you decide making the decision to use titanium oxide? And a second question is, how much would be the average cost for each straw if you make 1 million straws?
So to answer your first question,
We were planning on doing first silver oxide, but then we didn't have enough materials to make it, and so we didn't have enough time to make it. But that's as well in the further research. We might do that for different nanomaterial.
and we also planned to do silicon dioxide, which to create the nanoparticles, it was a very difficult process to make. And so we decided to do titanium dioxide instead, since that was just easier to do in the span of time that we had.
And then titanium dioxide is it's what gives white paint. It's like really white color. It's non-toxic. And since it's produced on the mass scale in the painting industry, I believe that it would be pretty cheap, although we don't know the specific cost.
It's also found in sunscreen.
Yeah,
Any other questions?
yes.
Okay, so this is a sort of thinking future. So the goal, so titanium dioxide, so the reason you're using the titanium dioxide is to make it nano rough, so you can try to make it super hydrophobic. But titanium dioxide is literally a rock. So it's not a plastic, but it's not biodegradable. So could you think about what you could do to make the same kind of structure that was entirely biodegradable?
We would probably use silicon dioxide because silicon dioxide it's basically just quartz. It's really abundant in the earth, so.
But it's also a rock. So it doesn't go away. I mean, it is titanium dioxide and silicon dioxide are both they're rocks. So
Yeah.
that part's sort of not so bad in nature, but they don't go away. So what does it need to do to be actually biodegradable? And what could you possibly do to do that?
So if we had more time, we would probably try to research other materials that are like such as plants, since plants are, certain plants have a hydrophobic surface. We would try to mimic that coating onto our straws, since that is also biodegradable. We didn't have enough time to obviously get that material, so for future research, that's what we would probably do.
Yeah, you didn't have anywhere near enough time. But if you could make nano rough out of paper and then make it super hydrophobic, it would still potentially not wet just because of its nano properties, even though it was fundamentally all cellulose. Okay, good job.
All right, group 2. Come on up, space ions. Yeah, you guys can go over there too and use that mic if you want to. You don't have to all crowd around here.
I'm Sihan.
Hi, I'm Allison.
Hi, I'm Heijun.
I'm Sonia.
And our experiment is measuring the elasticity of biopolymer gels. So what exactly is a biopolymer? So biopolymers are large molecules of repeating units linked together, and these are produced naturally by living organisms. And there are 3 main types. There's polysaccharides, which are sugars, polypeptides, which are proteins, and polynucleotides, which is represented by the image on the top right, which is DNA. And DNA is made up of nucleic acid monomers. And we have an image at the bottom that represents a polysaccharide or a sugar that is made up of repeating monosaccharide monomers. So these monomers are very important in creating this larger structures and larger networks of a molecule structure. And these structures are formed on the nanoscale, so 10 to the negative 9th. And so different arrangements of these structures can create different molecular shape and different molecular interactions.
Synthetic skin is a relatively new medical development, but is a rapidly growing subject. Our experiment pertained to 2 specific applications of synthetic skin, which were skin grafts and bandages. A skin graft is the replacement of healthy skin onto an area where the skin has been damaged, lost, or surgically removed. It can be used to treat skin infections, deep burns, large open wounds, ulcers on the skin, and skin cancer surgery, just to name a few. A bandage is a strip of material used to support or restrict the movement of the human body. Bandages are now starting to be engineered with biopolymers, as biopolymers have many useful medicinal and mechanical properties. For example, protein-based biopolymers increase cell proliferation, and certain biopolymers have adjustable permeability.
Okay, so currently in the market, we have a couple different products and procedures. So one product is hydrogel dressings and pads, and these are normally used to address burns. And these are made up of cross-linked polymers, which we will discuss later. Another product are bandages, like mentioned earlier, and these are just used for any cuts or wounds. However, for both hydrogel dressings and pads and bandages, they need to be replaced often and aren't able to stick onto the skin for long amounts of time. And artificial scaffolding or skin grafts use skin cells to help the body regenerate and heal. And scaffolding is basically nanofibers, so fibers on the 10 to the negative 9th scale, that use cell signaling to influence cell proliferation, differentiation, and biology. However, artificial scaffolding is pretty expensive, and it's mainly used for more extreme injuries. So currently, 3D printers are used to manufacture skin and muscles, and they use this by using biomaterials such as cells to create tissue-like structures by layering them on top of each other to imitate artificial skin. And Matroderm is a synthetic skin substitute that has recently been proven to be successful, and it was used with artificial scaffolding to improve flexibility and skin color. And this is made up of collagen and elastin, which are both biopolymers. And collagen helps facilitate new cell growth, and elastin allows tissue to resume their shape after being stretched. However, this is not available in the US currently, and it's also only used for more extensive extreme injuries.
So our research question is that how can we create a biopolymer band-aid with skin-like properties that can promote healing over long periods of time? And our hypothesis is that out of gelatin, agarose, and cellulose, gelatin is the best biopolymer for creating a band-aid with skin-like properties.
So the impact of our potential creation is that it could aid people with burns, cuts, and wounds. And it's more impactful than a normal Band-Aid because it can speed up the healing process, as that's a property of gelatin. It can encourage skin cell growth, which would cover the wound and make sure that it heals faster than it would normally. It can also act as a barrier to bacteria, as wounds often get infected, especially when they're deeply affecting the person, so it could prevent an infection.
So why do we choose gelatin, agarose, and cellulose for experiments? First reason is that there are three very common biopolymers. We can find them in the market easily. Second reason is that they are not toxic and have beneficial properties on human body. Like for example, gelatin contains healing properties and induces skin cell growth when applied. Agarose and cellulose are moisturizers and are compatible with the human body. The last reason is that all of them form gels that can be applied on wounds. And as you can see, the structure of gelatin is the picture on the top right, and agarose is in the middle, and the cellulose is the bottom one.
So one of the major mechanisms in this experiment is the mechanism of cross-linking. So cross-linking is basically when you form nanoscale connections between different polymers. So for example, like gelatin can cross-link itself. So gelatin can sort of overlap itself and form like a cross and then form bonds. So this makes the polymer stronger and more resistant to stress and high temperatures. So like in the top diagram above, like you see that blue line, that's the cross-link, and the two black lines, the wavy black lines, are the actual gelatin molecules, for example. And then the bottom is like the web link structure that actually forms like when you cross-link gelatin. So like, as you can see, like each of these points are different cross-linking areas, yeah. And an overview of our experiment. So what we did was we first synthesized these gels in Petri dishes. So we had to mix powdered gels in water, and then we had to melt them, make sure they formed gels, and then cool them afterwards. So that took about a day. After that, we measured elasticity. So we cut out small rectangles and then measured them, measured how far they would stretch before they broke. So like that video over there.
During the experiment, we started with gelatin gels, and we were successful in creating a gel that was firm yet elastic. However, we weren't able to synthesize a cellulose gel. When we attempted to, we found that it was insoluble in water, so we tried to add a cross-linker, NaOH, and we also tried glutaric acid, and then that didn't work. So we tried dissolving the cellulose in another solvent that was nonpolar, but none of these alternatives worked. Agarose gel did form, however, we determined it to be too rigid at all tested concentrations to be considered a viable skin substitute in regards to elasticity. For our agarose gel, among all our trials, we found that a concentration of 3% for agarose was optimal and then remained constant. And then for our gelatin gel, among all our trials, we determined that a concentration of 50% would be optimal, and then we found that elasticity decreased as we increased concentration.
So in conclusion, what we found out is that the gelatin was the most elastic biopolymer of all the ones that we tested. And then this one right here, the 50%, that one was the most appropriate for bandage application because it was stretchy enough to be able to fit any wound if it's like a heel where it has to stretch like around or something like that. But it also has the appropriate thickness and sturdiness that it can last a long time. In the future, we hope to replicate other properties of skin, such as adhesive qualities, thickness, and absorption, so that it replicates skin as much as physically possible because we want it to be comfortable. And then the results that we found suggested that a layered bandage would help improve efficiency a lot. So this is generally the plan that we were thinking about. So we would have gelatin as the base because of its healing properties, and then above it, we'd have a cellulose membrane. So we tried mixing cellulose with water and oil, but we think if we mixed it with a different substance that would help it become more of like a paste-ish liquid, then we could put it on the top, and that would be hydrophobic. So let's say you want to take a shower or go swimming. When you have this Band-Aid on, it wouldn't be a problem. Like normal Band-Aids, they just fall off, and they're not like and this would not do that. But on the bottom, then would have a semi-permeable adhesive. So that would mean it would stick to the skin for a long period of time, and no water would get stuck under there. And then, of course, the skin on bottom that it would go on. Thank you guys for listening. Do you have any questions?
Hi, that was a great presentation. What was the process for forming the crosslinks, and then how did you know that they had actually formed?
So cross-linking, basically, what happens is like when we dissolve the gel and we heat it up, and we start cooling it, it starts cross-linking by itself. And basically, you can tell it cross-links because it forms a gel. That's pretty much the basic idea.
Thank you.
Great presentation. Did you do any studies with like times or light or like the degradation of the material? Were you guys able to do any of that analysis? Any known findings?
Well, we did have a short period of time, so we synthesized the gels, and by the time the gels formed, we weren't left with much time left. So our main concentration in this lab was focusing on how we could get the gels to form, and then testing their elasticity. So unfortunately, we didn't get a chance to try the degradation, but also these gels are pretty hardy, so it would probably take a lot of force. But that would definitely be a good future test.
When you talked about the layering of the Band-Aid, any thoughts of what type of material you could use to maybe incorporate a medication or within any of the layers?
Actually, we incorporated gelatin, which by itself increases cell proliferation. So that means that the gel, it promotes healing, it promotes tissue growth. So that in itself would be like a medicinal property.
Yeah.
You wouldn't need any additional, anything else to incorporate.
But yeah, the gelatin does encourage skin cell growth, but there is a possibility that depending on what substance was used in the bottom, you could incorporate that. That would be a good topic for future research with more time.
Okay, so I got to ask a few more sciencey questions. Okay, so the first question was asking about what made the crosslinks. So for every different kind of gel that you looked at, there's a different mechanism to make the crosslinks. But for this one that you focused mostly on the gelatin, can you tell people a little bit more about specifically how they crosslink, like using chemistry?
Okay, so gelatin is a protein or a polypeptide. So when they form cross-linking, basically the blue line over there, they form peptide bonds because they're proteins. So that's how they cross-link with each other. I don't know if that.
Do the peptide bonds form the crosslinks, or do they make the black lines? So we got the blue lines and the black lines. And the blue lines are actually many things linked together in a long chain. Sorry, the black lines are many things linked together, and then there's also the blue lines.
The blue lines are more like hydrogen bonds. So the R groups of all the amino acids, they interact with each other. So it depending on the R groups, they'll form different bonds. So yeah, that's how they interact.
And that's exactly right. And then those bonds are weak bonds. And what's special about that in terms of how you process this? How did you use the fact that those bonds are weak bonds?
So because they're weak, we heated them up in water in order for those bonds to break at higher temperatures. And then once they cool down, those bonds would reform and then form a gel.
Yeah, that's exactly. And that's the really cool thing, is that you can manipulate them and break them and unbreak them, but they're unbroken at body temperature, but you can pretty easily assess where they are broken. So I just have one more follow-up question relating to the other person's comment about adding other medicines. So what is most of your gel made out of?
Gelatin.
What's the vast majority of it? Like by volume?
Water.
Water. So you got plenty of space to dissolve anything you want in all that water. And that's the super cool thing, is it's almost all water. You can put anything you want in there and it's still held. Good job.
All right, group 3.
Hello, everyone. Our topic is about water filtration and superhydrophobicity. And our project is to use wettability properties to filter pesticides from water. And I'm Han Yi.
I'm James. I'm John.
I'm Sarah.
I'm Lauren.
Okay, and today, and we may focus on one pesticide, and that is known as Roundup. It is a very common pesticide, and the active ingredient in the Roundup is glyphosate isopropyl salt. And about the Roundup, there is a controversy whether it will lead to cancer to humans. And of course, the company which produces Roundup will not see it is risky, but actually, according to many science organizations, it may lead to the cancer. And it may not lead to cancer, others may think. As for animals, it is slightly toxic. As we can see, here is the structure of the glyphosate. We can see it has 3 OH groups, 1 NH group, which make it polar and hydrophilic. 3 OH groups also make it acidic. It is nature that is the most acidic part may donate 1 proton to the most basic part. So glyphosate may look like this. But in the Roundup, actually, it's glyphosate isopropyl salt look like this. And according to these, glyphosate is corrosive, and also it may be harmful to the environment. Water filtration, we use activated carbon, and the carbon is processed to have low volume pulse, and it is available for adsorption. The glyphosate itself is small and it can easily pass through the filter, but with activated carbon, we can filter it. It's already proven that activated carbon can filter glyphosate. That's why we use activated carbon.
So here's a brief explanation of the wettability properties. So wettability basically means the measure the things the water adheres to a solid surface. So it has 4 properties: superhydrophilic, hydrophilic, hydrophobic, and superhydrophobic. What hydrophilic basically means water loving, which is water can dissolve in water, and hydrophobic means repels to water. And we usually use the contact angle between the liquids and the solid to measure the hydrophobicity of the liquid. If it is less than 90 degrees, it will be hydrophilic, and if it's greater than 90 degrees, it will be hydrophobic. So our guiding question is that what is the most effective way to filter pesticides out of water? So in our case, we use hydrophilic filter and hydrophobic filter. And we hypothesized that the hydrophilic filter with nanoparticles will remove more glyphosate than the hydrophobic filter, because water will pass through the filter, and the activated carbon would prevent the glyphosates from passing through the filter. And it is significant because it'll remove the glyphosate from the water, and it'll reduce toxicity in the water streams and prevent further pollution to the ocean. So we use two solutions in our experiment. The first one, we include 16.7% of Roundup, which is our pesticide. This means that we use 5 milliliters of Roundup plus 25 milliliters of water in our first solution. And the second solutions, we include 66% of Roundup, which means we have 20 milliliters of Roundup and 10 milliliters of water.
The first step for our experiment was actually synthesizing the nylon that we're going to use for our 4 different filters. And to do this, we took our hexamethylene diamine in an NaOH solution and Z-balkyl chloride in a hexane solution. And so we slowly mixed the two, and we formed this, as you can see here, with the 2 distinct layers. And at the intersection right here, the nylon was actually formed. And then from there, we used a glass stirring rod to swirl the nylon into strands, and then we put it in a jar, as you can see here. We did this 4 different times for our 4 different filters that we created. And then we also had to synthesize our silver nanoparticles, which we used to create the nano roughness of our superhydrophobic and superhydrophilic filters. So we heated a water bath to 80 degrees Celsius. Then we combined our 25 milliliters of silver nitrate with 25 milliliters of sodium citrate. And then we heated it using the water bath and stirred it with a magnetic stir bar. And we waited for the solution to turn a light yellow color, which meant that the silver nanoparticles had formed in the solution. And then we also had to functionalize our nylon to give it the wettability properties that we desired for our 4 different filters. So the first filter we made was our hydrophilic one, which was just made from regular nylon, because nylon is naturally polar, which makes it hydrophilic. And then we made a hydrophobic filter by adding iodocantane to it, which made it nonpolar and hydrophobic. And then we made a superhydrophobic one by using octanthiol as our nonpolar group, and then we added silver nanoparticles, which provided the nano roughness that aided this make it superhydrophobic. And then we made a superhydrophilic one by taking regular nylon and adding silver nanoparticles.
So these are 2 filters that we made in our glass pipette. So for the hydrophobic filter, it was cotton to keep the nylon filter in place, and we functionalized the nylon with iodocantane to make it nonpolar, making it hydrophobic. And for the hydrophilic filter, it was just cotton with nylon, and because nylon is hydrophilic, we didn't have to do anything else to it. For the superhydrophobic filter, it was the cotton, and then we functionalized nylon with the 1-octanethiol, and we soaked it in silver nanoparticles to give it the superhydrophobic. And for the superhydrophilic filter, we did nylon and soaked it in silver nanoparticles to increase the surface area to make it superhydrophilic. So for our filtration system, we added activated carbon into our solution, and what activated carbon does is that it attaches itself to glyphosate, and this prevents glyphosate from filtering through with the non-acidic solution that comes out. And we tested these filters by suspending our pipette filter over the jar and putting our solution and pushing air through it so the yield would come out.
So this is the data that we collected from our experiments. And we measured pH because the pH of pure Roundup is acidic, which is 4.58. We originally planned to do 4 different concentrations, but with the limited time and the long process it took to filter the concentrations, we only did the 2 extremes, 16% concentration Roundup and 66% concentration Roundup. And the pH for the 16% was 4.81, and the 66% was 4.62. And after filtering it through the 4 different filters, we got the numbers in the middle pH column. And the last column shows the change in the pH from before and after the filtration. And we can see here that the hydrophilic filter was consistently the most efficient for both concentrations. So we came to a conclusion that the hydrophilic filter, the filtered solution for the hydrophilic filter was closest to neutral pH, which is 7, and it filtered out the most Roundup, which shows that our hypothesis was only partially correct because we hypothesized that the hydrophilic filter with nanoparticles would be the most efficient. And from this bar graph of the pH of resulting solutions, we can see that there's a pattern. So the hydrophilic was consistently the most efficient for both concentrations. So some possible errors that we might have had is pH measurements. Because it took such a long time to filter out the solutions, we only had a small sample size and we're not able to use the pH meter. So we used the pH paper, which might not be as effective. And also when we used the pH meter for one of the solutions, we saw that the numbers we got were kind of different, so that could have been a possible error. Also, we could have incorrect functionalization, but we would not know because we did not test the wettability of the filters. So some future directions could be having more time to filter more solutions so we could use the pH meter, and using all the different concentrations instead of the two extremes, and also measuring the contact angle of the filters to see if they have the correct wettability that we desire. Thank you. Any questions?
Thank you. That was an excellent presentation. Did you look ahead to see how you might use this for filtering large amounts of water like groundwater, where pesticides and pollutants are a significant environmental problem?
So yes, that is the major application of what we were studying. So currently it's proven that activated carbon does help with the filtration process of glyphosate along with different other pesticides. But we were testing to see if there was a more efficient filter design that we could use wettability properties, just make the process more efficient and effective.
Any other questions?
So did you time how fast the different filters went?
We were going to, but then we thought that would be too many variables. But we saw that the hydrophilic was the fastest. We got through both of the concentrations before the other filters got through the first concentration.
And so how do you interpret that? In terms of the earlier question about actually using this for real groundwater remediation, how is that result important?
Well, the hydrophilic filter, as you can see, was the most efficient. It got most of the Roundup out, and it was also the fastest. It was the fastest time for getting rid of the Roundup, and also it was closest to neutral pH. So if we were to filter out a larger amount of Roundup in the real world, then we would use the hydrophilic filter.
Yeah, there's lots of good filters that work, but most of them are just way too slow for real water treatment. So speed is a super important variable. Okay, good.
All right, group 4.
Hello, everybody. I'm Marissa.
My name's Sonia.
I'm Jay.
I'm Monty.
And I'm Brandon.
And our research project is on changing the capping ligand to observe ferrofluid properties.
So to start us, wrong slideshow. So to start us off, let me explain what a ferrofluid is. So ferrofluids are fluids that contain 10 nanometer thick magnetite particles that are suspended in a liquid such as water or oil. Now 10 nanometer thick basically just means that it's super, super, super small particles. So these ferrofluids will magnetize in the presence of a magnetic field, and therefore they are attracted to magnets. As you can see in that picture right there, that is a ferrofluid that is in the presence of a magnet, which causes it to spike. So a couple of current applications for ferrofluids that are being used are in medicine, cooling speakers, lubrication, and rotary seals.
So as Brandon said, these nanoparticles are super, super small. So what we have to do is we have to cap them in order to preserve their nanoparticle properties. And so to do this, we use a capping ligand that is either polar or nonpolar in order to control the nanoparticle growth. So the two different capping ligands that we were using were one that was nonpolar and one that was polar. So a lot of us are familiar with the concept that like attracts like or like dissolves like, which is similar to what we used in our experiment, just like how oil and water don't mix, nonpolar and polar substances do not mix. So we were testing the properties of these two different types of capping ligands.
So our research question is, would altering the capping ligand of a ferrofluid change its properties? We tested this by testing ferrofluid as a lubricant and testing ferrofluid as a filter.
So since we have two experiments, we have two hypotheses. Our first one for the lubrication is that when we use oleic acid as a capping ligand, the commercial ferrofluid will work more as a better lubricant. And for our second hypothesis, if the capping ligand is oleic acid, the ferrofluid will only interact with nonpolar substances, and if it's mercaptopropionic acid, it will only interact with polar ones.
All right, so the impact of our research is, our research will show us if changing the capping ligand, our research will show us if changing the capping ligand changes which substances like ferrofluids interact with. This can be utilized when ferrofluid is a lubricant because we'll know which either polar or nonpolar ligands will work better for lubrication and reducing friction. This can also be utilized to separate polar substances from nonpolar substances like oil and water.
So for our first experiment, we tested ferrofluid as a lubricant on various surfaces.
So the general gist of our first experiment is that we used two different ferrofluids, a water-based one that we made ourselves and a commercial one that we bought online. And we used a control with no ferrofluid. And so what we did is we slid it down a ramp right there, as you can see up there, and recorded the time it took to go down the ramp. The ramp was 1 foot long, and we divided that 1 foot by the time it took to find the velocity and compared those. We have a constant force applied to the block, or applied to the cube sliding down being gravity, so it was, there was little error in that regard.
So as you can see on our graph, for our control, where we did not put any lubricant on the magnet at all, the times vary wildly because it would do things like roll because there was no way of it sticking down. But for the water-based and oil-based lubricants, you can see that the times were much more consistent. But you can also see that the water-based lubricants were much worse in terms of reducing friction than the commercial ones. Two possible explanations for this is we made the water-based lubricant ourselves, so it may not have been as high quality as the oil ones. But also the magnetite nanoparticles fell out of suspension much easier in the water-based one than they did in the oil-based one.
As you can see right here, what we did to find the velocities is we took the average of the times and then divided that by the distance. And as you can see, the commercial ferrofluid went down much faster and had a velocity of 0.625 meters per second.
So here are some errors, some lessons and improvements for future experiments with ferrofluids. So as you can see in this picture with the purple glove, we have our magnet coated with ferrofluid. However, this ferrofluid had already dried up, and so in future experiments, we would like to make our ferrofluid with a substance, a suspension fluid that would not evaporate as quickly. In our experiment, we use hexanes, but in commercial products, they typically use things like kerosenes to make it so that it would not evaporate as quickly. And this picture shows a comparison of our ferrofluid versus the commercial product. Now, another error is shown in this ramp. As you can see here, we have our ferrofluid dried on the ramp. Now, this interacted with our magnets as they were falling down, and it caused inconsistencies in the actual speed as they're going down. To combat this, we would use new sheets of foil on the tracks after each trial.
So our second experiment was testing how polar and nonpolar ferrofluids interact with oil and water in terms of separating the two.
So in this experiment, we took a petri dish and mixed oil and some water. We dyed the water red so you'd be able to see. And we basically used our 3-mercaptopropionic acid, which was our polar ligand. And then we placed the magnet under the petri dish. And as you can see in the image, it's pulling the water along with it, and the oil is left behind.
So then we used oleic acid as our capping ligand, and this ligand is nonpolar. So we dyed the water green in this test, and when the ferrofluid was added to the oil-water mixture this time, it was clear that the ferrofluid and the oil aggregated towards the center of the petri dish, and the water separated itself around the oil and the ferrofluid.
And although there were interactions between the different ferrofluids and their respective substances, the magnetic nanoparticles were not able to completely separate the two substances. They could only drag some of it with it. So they did not bind enough with the molecules to, to drag it, causing some oil to escape, which you can see up there. And in the future, we would like to run more tests along these with these substances, along with different ones to see what kind of interactions can be made. And we would also like to test these same interactions at a larger scale so they would have more real-world applications and to see if they would still work at that scale.
So through these experiments, we learned that changing the capping ligand does in fact change the ferrofluid properties. In experiment 1, when we used oleic acid, the nonpolar ligand, the ferrofluid served as a more effective lubricant for the magnet. In experiment 2, we learned that the nonpolar and polar capping ligands are shown to interact with their respective substances.
So in our first experiment, we tested ferrofluid as a lubrication. So here are some future applications for ferrofluids. We could use ferrofluids in industrial machinery as a lubrication, as it is shown to be very good at lubricating surfaces. Now, we could also use it for possibly more efficient transportation in trains and cable cars. So the ferrofluid as a lubricant would reduce the friction of your train or cable car, which would cause it to move faster and require less energy to run. Now, our third application for ferrofluid will be in permanent magnet motors. So as you can see in this diagram right here, the permanent magnet motor is made of a rotor and a stator. The rotor is made of many different permanent magnets, and the stator emits magnetic field that interacts with that field of the magnet in the rotor and causes it to spin. So ferrofluids will be used here as a way of lubricating it to make it go faster, as well as a way to reduce the air gap between the rotor and the stator, which would reduce the loss in magnetic flux with the rotor and the stator and make it overall run more efficiently.
Okay, so possible future applications for our oil, ferrofluid, and water separation is we could separate oil from water in oil spills in order to use a nonpolar ferrofluid to take the oil out of the water, or vice versa in an engine where water has gotten into the engine and we need to remove it without removing the oil. This also has applications for separating different polar and nonpolar substances from each other than oil and water.
All right, thank you for your time. Any questions?
Okay, so you were looking at trying to use these for separating oil and water, and there's a lot of interest in using this for like cleaning up oil spills. But so what's the challenge in terms of the environment of using something like a ferrofluid in that way?
One possible challenge with this is some of the magnetite nanoparticles might get into the environment, which could be pretty bad if that does happen.
So that is the challenge, is anytime you add anything, you don't know where it goes. The idea is if you can make them oily, they'll stay with the oil. Then so you have some good ways to potentially get rid of most of them. Can you tell us a little more about that?
Can you repeat the question?
The big challenge, anytime you add anything to clean something, you can do more damage than you do good by getting your cleaning agents into the environment. Okay, so in this case, your goal is to say, can we make the nanoparticles stay with the oily part? Then can you talk more about how you're going to remove all of that, the oil and the nanoparticles?
Using probably a large magnet, because the oil will bind with the nanoparticles in the ferrofluid. So a large magnet would collect both the oil and the ferrofluid.
Which is really easy in the lab and a little harder on an ocean.
Right, yes. Yeah.
So what is your sort of one good hope in terms of the fact that they can potentially get into the environment? Fundamentally, what is magnetite?
Iron oxide.
And if you were going to like explain to your 5-year-old sibling what it was, what would you call it?
I don't really understand the question.
I'd go for a rock. So it is a natural just rock, literally. All the ites are rocks. So that's a good thing. It is actually a natural occurring mineral that you can find. And there's iron oxide pretty much everywhere. So those are positive aspects of sort of using it for environmental cleanup. Okay, so now I've given you guys all lots of time to think. Now other people get to ask a question.
So the way we made it was we used iron, FeCl2 and FeCl3, and we had solutions of both of those, and we mixed them together. Then we added ammonium hydroxide to start forming the magnetite itself, and then at a certain point we added oleic acid, which not only acted as to repel the water, but also it acts as a capping agent, which stops the nanoparticles from growing any larger.
Okay, so this is your, when you're talking about synthesis, here's your quick lesson. Okay, you said you use FeCl2 and FeCl3. What were they? What was their goal? Why'd you use them?
We needed the iron.
They're just a source of iron. So when you're saying something, we used FeCl2 and FeCl3 as a source of iron.
Yes.
And then used ammonium hydroxide as a source of?
I'm guessing oxygen, but I don't fully understand.
The hydroxide is OH, and it takes the oxygen from the hydroxide. So that's your source of oxygen to make iron oxide. And for everybody, when you give your syntheses, if you just say those extra few words, then your audience will have a way better understanding of why you did what you did.
Any last questions? And if not, then let's thank our group. So I'm going to switch up the schedule slightly and have one more group present before the break. So group 5, Pro Hydro.
Hello, so our experiment is about superhydrophobic prosthetics and their ability to prevent corrosion by me, Caitlin.
Me, Avi.
Me, Aaron.
I'm Nadia.
I'm Estelle.
And our goal or main objective is to create a superhydrophobic coating that will prevent corrosion of prosthetics. And to give some background on prosthetics, they are made out of titanium, aluminum, and other metals. And they are medical implants, such as dental implants, to improve mobility, manage daily activities, etc. However, there are some current issues with prosthetics, such as the biomaterials that make them up. They should contain sufficient mechanical strength to avoid fracture. However, the repetitive exposure to impure water contributes to corrosion. And in addition, the degradation of metallic implants occurs when placed in hostile electrolytic environments that can lead to postoperative implant-associated infections. And last but not least, since water is able to seep into most implants and prosthetics, this then shortens the longevity of the implants and in addition to the stability. And if you look at the photo right there with the two prosthetics submerged in water, some prosthetics are in fact waterproof, but they can go up to about $50,000 and last roughly about 3 years. So this then leads us into our areas of investigation, and in the scientific community, they're trying to figure out how to develop superhydrophobic implants that are bacteria resistant and a surface modification of the biomaterials, such as coating techniques, which makes use of the superior properties of nanomaterials that lead to a better, improving biocompatibility.
So in contrast to a regular hydrophobic surface, a surface is characterized as superhydrophobic when a water droplet is able to fall on it and form a contact angle between the water droplet and the surface that is on that exceeds 150 degrees. So all levels of hydrophobicity are measured by a contact angle, which is the angle made between the water and the surface that it's on. And superhydrophobic surfaces can only be made if they are coated with a hydrophobic substance and are roughened, and if the surface is roughened at the nanoscopic level. So all of our coating that we're using in our experiment is superhydrophobic since we need our materials to be water resistant.
This then leads us into our important question on how does superhydrophobic coating of metals respond to corrosion in water environments with varying pHs? And we chose a varying pH from 5 to 9 because this is the range of pH of water that is naturally found across the world. And then our hypothesis is that we hypothesize that the superhydrophobic copper that is coated in DCT, titanium dioxide, and never wet will undergo minimal corrosion, whereas the uncoated copper in the pH 5 that is a solution with nitric acid and water will undergo the most corrosion.
So we used nitric acid in our experiment to lower the pH of the water that we submerged our copper samples in, because the copper we used is reacts with nitric acid and is highly corrosive, and the nitric acid is highly corrosive to the copper. So the equation above shows the oxidation reaction that takes place when copper is in the presence of nitric acid, and we predict that this reaction will occur the fastest in our uncoated copper sample because that's the only sample that does not have a superhydrophobic barrier between the pH solution and the copper surface. So some potential medical and economic impacts that can result from creating a superhydrophobic surface for prosthetics include increased longevity of the prosthetic, reduced infections related to the prosthetic, and reduced costs because if we have a superhydrophobic coating for the prosthetic, people can buy prosthetics made out of cheaper material rather than expensive waterproof prosthetics and just spray the superhydrophobic coating on top of it.
So in our experiment, we used 3 different coatings, and each of these hinge upon the fact that we use nanoparticles in order to induce superhydrophobicity, which basically stops any kind of water or acid or anything else from touching the metal on the inside. So our first coating was a DCT coating, and in order to do this, we first took our copper slides, sanded it down in order to remove the oxide layer, then submerged it in silver nitrate in order to create silver nanostructures, and then submerged it in DCT in order for the DCT nanoparticles to bind and with their nonpolar tails create the superhydrophobic layer. The next coating we use is titanium dioxide, where we synthesized our own titanium dioxide nanoparticles. And this is by soaking it in acetic acid and by grinding it down for about 25 to 30 minutes. And in this time, these rather large titanium dioxide particles go into their nanostates. And in order to keep them there and stop it from aggregating, we added an oleic acid capping ligand in order to preserve the unique nanoscale properties. And finally, we use the Never Wet spray, which is a commercially available spray, in order to compare with industry standards and to see how our products stand up to what's there in the market already. And finally, our control for this whole experiment was uncoated copper, as this would provide the best baseline in order to see how good our coatings are, and as we can see how much corrosion occurs before and after submerging it in different pH solutions. And as you guys can see, that is our uncoated copper. It looks kind of smushed because uncoated copper is hydrophilic, whereas you can see the Never Wet, the DCT, and the TiO2 have a lot better beating up because they are superhydrophobic surfaces.
So as we could not really measure the contact angle just by eye, we decided to use an optical tensiometer, which allowed us to take zoomed-in pictures of the water droplet on the hydrophobic surface and then measure the contact angle by setting points on a computer. And so those are the pictures that we took. As we can see, the encoding copper has an angle of 84.31. So this shows that it is slightly hydrophilic. And the other coatings, the Never Wet, TiO2, and DCT, all have hydrophobic angles, and the DCT is nearly superhydrophobic. And the red lines that we unfortunately cannot really see were the points that we set to measure the contact angle. And we also measured the mass to determine the corrosion as to quantify the corrosion. And as we can see it in coated copper, because it has nothing on it, it has a very small standard deviation. But the Never Wet, because it was a spray, the coating was uneven, and that caused the standard deviation to be quite large and maybe affect the results.
Okay, so we created water of different pH levels by adding nitric acid to lower the pH of the water and sodium hydroxide to increase the pH. pH was recorded constantly whilst adding the acids and bases by the use of the pH meter, which can be seen on the right. The dilution of acids and bases allowed us to obtain pH levels of 5, 6, 7, 8, and 9, which we use for experiments. So the next step in our experiment was to submerge our copper pieces into each pH solution we made. For each row, you can see a different coating that we used for the copper, and each column has a different level of pH. Furthest left being 5, going up one at a time, all the way to the right to 9. They were submerged for 18.5 hours, although this picture was taken only 5 minutes after we submerged them.
And so after leaving the samples in for 18.5 hours, we measured the contact angle again. And what we found is that DCT remains superhydrophobic, as we can see on the graph. So it is the best coating. And copper, the encoded copper, had the lowest hydrophobicity and the highest standard deviation. So some of the samples were really hydrophilic and corroded a lot. And so then we also plotted the contact angle against each pH. And what we found is that at pH 5, there was a large decrease in contact angle before and after submersion. So that might mean that increased acidity
increases the reduction in contact angle and thus increase corrosion. And when we zoom in to look at only DCT and uncoated copper, so the best and G control, we can clearly see that there is a drop in contact angle at pH 5, but also that at pH 7, this is where there's the least change, and that might be caused by the fact that it's just water and there's no acid or base in the solution. So after calculating the % change in mass for each copper sample, we found that the difference between the final and initial masses of the copper pieces were not significant enough to indicate corrosion. However, the uncoated copper, the never wet, and DCT coated samples had a very slight increase in mass, while the TiO2 copper had a decrease in mass. And we think that this happened because when the TiO2 copper pieces sat in the pH solutions overnight, the TiO2 film on top of them degraded, therefore accounting for the decrease in mass. So similarly, when plotting the mass change of the copper samples against the specific pHs they were submerged in, it was apparent that the pH did not significantly affect mass change except in the TiO2 sample, like I discussed in the last slide. However, the mass change results for the TiO2 samples were most likely anomalies that resulted from the degradation of the TiO2 film after leaving it in the acidic pH solutions overnight. However, more trials would need to be performed to confirm that these were in fact anomalies.
And we can see that our uncoated copper in both the pH 9 and the pH 6 solutions have corrosion. As you can see that the shiny copper oxide layer has completely gone. Further, there are darker spots which indicate corrosion as well. The DCT is actually not corroded. That's actually just the silver on the coating. So the metal was more or less unharmed, as we could tell from our mass data, and the never wet and the TiO2 also held up pretty well. However, we did have a couple of sources of error during our experiment, and the first one would be related to our TiO2, because our TiO2 on application and after it dried, it started cracking, which basically left holes for the solutions to go in and actually interact with the copper, thus corroding it. And so in the future, we should probably look into a different capping ligand, which can give our solution a different viscosity so that it can actually spread well and not crack. The other aspect of the TiO2 is that it actually, the suspension liquid or the suspension agent that we used was acetic acid, and that actually started reacting with the copper. As you can see, the copper slides in the picture are actually blue, whereas TiO2 is actually white. So maybe in the future we need to look at a different suspension agent that doesn't actually react with the metal it's coating. Another source of error was that a couple of the surfaces that we were testing were actually so super hydrophobic that we couldn't physically put water droplets on it in order to check the contact angle. So in the future we should probably look at oh my, is this playing? Oh, it is. All right, yeah, you guys can see how the water droplets roll off. And so basically in the future, we should probably be able to get slides which are perfectly flat so that we can actually measure our contact angles.
Okay, so we conducted a further study with the nitric acid to represent long-term corrosion in the limited time frame that we had, which is 2 days. We can see that the nitric acid in fact reacted with the uncoated copper, DCT, and TiO2, except for the never wet. And the TiO2 and the DCT, in fact, became hydrophilic, but the never wet stayed hydrophobic.
And so after submerging them also in about 18.5 hours, we did a UV visible spectrophotometry, which basically means that we recorded the wavelengths at different absorption, and so we could really plot a graph like this. But the only problem was that the solutions that we took were too concentrated, so we couldn't actually plot the graph and record the absorption. And so in a further study, we would have to get more dilute solutions in order to get a better graph and actually be able to observe the corrosion through the absorption spectrum. So we concluded that DCT was the best coating to reduce the corrosion of prosthetics, and we came up with that conclusion because DCT was the most super hydrophobic, and so it was the best to prevent short-time corrosion. But we also concluded that uncoated copper was the one who corroded the most at pH 6, which we originally thought was pH 5, but when we look at the loss of superhydrophobicity, it was actually at pH 5, so we can say that our hypothesis is partially correct. And the TiO2 coating that we did was not really effective, so we would need to do further tests to get a better and a more even coating. And overall, we can say that the coating produces a better performance in terms of reduction of corrosion and preventing loss of superhydrophobicity for all the coated samples, which is really promising for future research.
All right, and now some improvements on our experiments. So due to our limited time frame, we weren't actually able to simulate longer periods of time in which we could put our metals in and check our surface coatings. So a possible improvement could be that we can maybe increase the time that we leave our surface coatings in solution from because in this experiment we left it for around 18.5 hours, but we could leave it over weeks and maybe months and collect data, and that might be that might lead us in a different direction. Further, only copper was used because that was the most easily available metal that we could find. However, prosthetics are not actually made of copper, so we might have to look into silver, aluminum, titanium, and stainless steel, which are all materials that prosthetics are actually made of. Another aspect of our experiment which kind of changes our conclusion is that the NeverWet is actually not ingestible, so we can't use it in prosthetics which are implants. So for example, dental implants, you can't put them in your mouth because of ingestion problems. And so maybe finding some solutions which are actually non-harmful for humans would be another direction we can take this experiment in. And finally, our titanium dioxide coating was not efficient, both due to its suspension agent and its capping ligand. So further research needs to be done in order to find more efficient alternatives for them.
Thank you
All right,
very much.
thank you.
So you use 3 different materials. Some they have chemical names like TiO2, but some they have commercial names. Are there a difference between these materials in terms of how easy to obtain, how cheap or expensive they are? So in terms of practical use case.
Right.
Yeah.
Can I take this? Or
Sure,
you go.
take it.
Okay. Okay. So the DCT and the titanium. Okay, titanium dioxide is actually what you find in paint, so it's actually relatively cheap and it's not all that expensive. The DCT, on the other hand, is a little more hard to find. The commercial NeverWet sprays actually have a blend of aluminum. I think there's iron in it.
Silica.
And
I think acetone.
Acetone,
Yeah.
right? And so I don't actually know how they produce that and what the costs are for that. But for the other two, they're actually not that costly. And if we look at it in the grand scheme of things, instead of buying waterproof prosthetics, which are $50K every 3 years, you can buy something which is under $10,000 and repeatedly apply these sprays, and which would probably not even reach $50,000 over the lifespan.
Yeah, and as we said, the NeverWet spray is just available in any store, so you can just buy that, but you cannot put it in an implant, so dental implants. So we were trying to find a solution, another solution that would work for internal implants.
So thinking about real-world applications, I was thinking about durability of the coatings from an abrasion resistance standpoint. Is that something that you considered and showed up? It seemed like some of that TiO2 might have been subject to some of that. And one of your early slides had, looked like a hip replacement piece where that could be applicable as well.
Yeah, so we didn't really look at abrasion, but the TiO2 coating definitely just fell apart, so it would not be sustainable for a long time. So we need to find a way to coat it and make it an even surface so that it actually resists corrosion and abrasion maybe, but that would definitely be something to test.
Further, our experiment was mainly like targeted at how can we decrease corrosion. So we didn't actually have like the time nor the materials to actually research how to make these surface coatings like hard enough to like withstand like a heavy usage. So we were only looking at the corrosion aspect of it.
Thank you.
It's a great experiment. I'm just curious how good you maintain the pH. Did you measure it, before and after the experiment? Is there any pH change? I understand you use nitric acid and sodium hydroxide to create the pH of the water. Thank you.
Okay, so.
Try to mix around you answering the question. Let everybody answer the question.
Okay, so what we basically did was we took distilled water and we added either the acid or base to alter the pHs that we need. So we basically just diluted the acid with water until we got our the desired pHs that we needed for the experiment.
In addition, we used a pH meter just to be precise and accurate with our pHs to make sure that they were right on.
Did you measure after the corrosion?
No.
In the wells?
No, we didn't really think about measuring the pH afterward. That would have been a very good idea. So in future research and experiments, we should definitely do that. Thanks for the, yeah.
That means I have to know how to turn it on. Heaven forbid. One of those two. Okay. No, it's for the live stream. You can't hear it if you don't have the mic. That's actually a really good point because the corrosion process can change the pH. So if it was long, you don't know. So first, a comment for everybody. Lots of people are asking questions, and people are saying, well, we didn't get to that. Of course you didn't get to that. You had 4 days to do the whole experiment. A PhD takes 5 years, and you had like a tiny fraction of a week. Of course you didn't get to tons of things. Don't feel guilty when you say, sorry, we didn't get to that. It's a short summer program. The whole first week we were teaching you like how to be a scientist. Then you got to actually do it for a short amount of time. Okay, so my question for you is, so you did an experiment that I thought was a great experiment where you dunked them in concentrated nitric acid. No prosthetic will ever meet concentrated nitric acid. Why was that a great experiment?
So basically what we wanted to do is that because we had such limited time, we wanted to put it in concentrated nitric acid to kind of represent the the repetitive exposure to nitric acid or to acidic water, and to make it just like in short time and to maybe test the resistance in like nitric acid, even if it's it won't be exposed to such concentrated nitric acid, but it's still useful to know if it can resist that much.
So that's right. But basically a thing to say is that more extreme chemical conditions is equivalent to much longer time at less extreme chemical conditions. And so when you don't have time, when something's supposed to last for years and you don't want to test it for that long, what you do is you make it a more extreme case and then you do a shorter amount of time. And you say, oh, a little time at these crazy conditions is equivalent to years at more normal conditions. And people do that for everything, batteries, solar cells, bio things. And so that was a great example of what people do to test long-term stability when they are not that patient. Okay, another awesome job. And now Rita has some announcement.
Well, basically basically just one announcement. So we're going to take a break for about 10 or so minutes. So everyone please relax. There should be some snacks outside, and we'll be back in 10.
Thank you, everyone.
All right, so we are going to continue on with our presentations. So if Team Muskie can come up.
Wait, my mic goes here, right? Your mic
Okay,
goes
yeah,
here?
we're gonna use yours.
Cool.
Do the lineup, do the lineup.
Are you gonna use
We all
yours?
crowd on this one.
Which one? Sure?
Yeah, we all use this one. Because this
Okay.
is too low. Wait, test.
Just use it. Wait, it works.
Okay, no, like, but like the high.
Oh yeah, that's fine.
That's good. That's good.
All right. So our experiment is on the effect of pH on dye-sensitized solar cell efficiency. And I'm Owen.
I'm Tianjun.
I'm Daniel.
I'm Isha.
And I'm also Isha.
All right. So since the energy crisis is occurring, the amounts of fossil fuels in the world is steadily decreasing. So we need many forms of alternative energy, one of which is solar cells. Currently, silicon solar cells are used as a main device to get approximately about 25% of the light from sun and convert it into energy. The silicon solar cells are very expensive, however, and most people cannot afford them. So, as an alternative, dye-sensitized solar cells were created, which are cheaper and less efficient solar cells. These solar cells are made of natural dyes, including beet juice, and they are cheap, environmentally friendly, and biodegradable. So the significance of solar cells is that currently silicon solar cells are way too expensive for many people to afford. So if we were to make dye-sensitized solar cells more efficient, more people would be able to use them and change from the fossil fuels onto solar cells, which would greatly decrease the greenhouse gas emissions and save fossil fuels.
So the question that we researched was how do varying levels of pH in the anthocyanin dye of a solar cell affect the amount of current generated? So we researched pH because most of the other aspects of like the solar cells, like the wavelength of the dye or like the color of the dye, that was already like widely known. So like we decided to test the pH of the dye. And so we hypothesized that if we decrease the pH in the dyes of the solar cell, the current produced will increase because lower levels of pH create more ions, which have more excited electrons, and like the more electrons there are, the more energy that they will absorb and produce. So yeah.
Okay, so to help you guys better understand our experiment, I sort of put together a diagram, and you can see that we need 2 conductive glass slides, and the conductive side, because there's only one conductive side, of the glass slides are both in between the other materials, and then we coat carbon, which is in the form of graphite from pencils, onto one of the conductive sides, and then we coat the chemical TiO2, which is already said in all the previous experiments pretty much, on the other conductive slide, and we add a layer of iodine and the beet juice dye that we're using. So normally when a light source comes in, it usually comes from the top. So a electron from the light source, it will come in from the top. It will be attracted by the beet juice dye, and it will be excited so that it can jump onto the conductive slide, and then through the help of an outside source, which in this case we use the clamp, it will travel all the way around and then end up on the top side pretty much, and then it will go back downwards again, but this time it will go into iodine, and it will cause a redox reaction, an oxidation reduction reaction, which will allow the electron to flow through the iodine, and the carbon essentially acts as a catalyst, or this redox reaction would never happen, or it would happen, but it would take very slow and it wouldn't be efficient, and so that's how we get the electric current flowing. And right now, if we add another external source to the side, it will pretty much be powered by the flow of electrons. And this is how we put together our solar cell. Is to give you guys a better understanding, this is how we put it together with the dye on one side and the carbon on the other side. And then we put together like this with like a little edge on the ends to clamp, so we can clamp the electrical current multimeter onto the sides to allow electron flow. And then here's the clips I talked about with the iodide solution in between the cracks. So we will drip it in there and then wait till it seeps through, so we will get an even layer. And after we assembled the solar cell, which looks like this, we will measure the current with the multimeter, which is right here. And I don't think you can see in this picture, but the red and the black wires will have little clamps that we will clamp onto here and here. And then we will shine a light through it, which is either the flashlight or the projector. Those are the light sources that we used in our experiment. And we will repeat this process. We use a different range of pH, 4.7 to 6.7 in 0.5 intervals. And then we make the different pH dyes by adding acid or base, these two acid or base, 1 molar HCl or 1 molar NaOH. And then we keep track of the pH by using this pH meter, which is this, and this machine in the background. And one thing I should mention is that we use beet juice just because, or not just because it has anthocyanin, which is what we want to use in the dye, but also because it doesn't change color drastically under this range of pH change. So maybe it will change color on the bigger pH change, but then not on the ones that we're testing.
So, like Robert said, we collected data using 2 light sources, and one was a projector and the other was a flashlight. So the reason we didn't use sunlight was because since this is just preliminary research and we only had 2 days to do it, in like a perfect situation, we would test it over a long period of time in sunlight, so we would get a better reading of current, and small factors like clouds wouldn't greatly affect our data, whereas if we did it over 2 days, our data would be skewed. And so when we tested the pH of the beet juice, it was 6.2, so this kind of acted as our control. And we went up in increments of 5 so our research showed when we researched online, we found that lower pHs are often associated with better current and so better efficiency. So we decided to conduct in increments of 0.5, 3 times below. So we did 4.7, 5.2, 5.7. So we tested more acidic levels rather than basic levels, since we only tested 1 basic. And what we found was that there tended to be a more optimal pH, and this happened around the pH of 6.2. As you can see in the graph, at 6.2, our graph seems to have a higher current produced. So in our first trial, our very first trial, you can see we kind of have an outlier at 6.2. This was because it was the very first solar cell we made, and we weren't as used to making it, and there were some errors that happened. But when we did it for the second and third trial, we found that results greatly increased, and this is because 6.2 was the optimal pH. And on this graph, this tested the flashlight, and you can see here again 6.2 is the optimal pH, and it gave a current of 4.1 microamps and 3.2 microamps. And so what we concluded was the optimal pH was indeed 6.2 for the best efficiency. And you can also see in the graphs that at 2 acidic levels, the current produced is super low, and at too high of a pH, the current produced is also low. So we found that if the pH is too high, that it was due to a chemical deformation in the structure of the anthocyanin dye, and it was more specifically in the flavillum cations in the anthocyanin dye. So anthocyanin is the colored part of the beet juice. And because there were a lack of flavillum cations, which is the part of anthocyanin that absorbs light, this is, if there's less of these cations, it will absorb less light. And because there's less absorption of light, there's less current produced, therefore it's less efficient. And with the lower pH, we found that too low and too acidic of a pH, it starts to degrade the properties of the dye. And so what we found is that after the maximum efficiency pH, acid starts to lower solar cell efficiency.
Okay, so we conducted this experiment because it can be applied at a much larger scale, such as in fuel and energy to power your cars, such as a Tesla, because we're Team Muskie. Shout out to Elon Musk. And it can also be used to power your small devices, such as your phones, calculators, computers, and batteries. And the dye-sensitized solar cells can also be applied to windows on the side of buildings. And it was, when we looked up on our research, we found that in a past experiment, to keep it real brief, it was found that a circuit module was modified with dye-sensitized solar cells, and that the module with the parallel circuit generated voltage that tended to be constant, which resulted in small efficiency compared to the module with a series circuit. So the series circuit had a higher efficiency, which shows that this is a much cheaper alternative to the silicon solar cells, which are really expensive today. And so in our further experimentations, since we only had 2 days and we could only test only pH, because we could have tested higher pHs, because like Robert said, lower pHs don't change the color of the beet juice when in the specific pH range that we tested. And we could also test it in a different light source, such as sunlight, because we only used the projector and the flashlight. And sunlight is more relatable because it's a daily life thing that we all are exposed to, and it could be more useful information for the future. And we could also test different catalysts. So we use graphite as our catalyst in the solar cell. So we could use something like nickel or chromium, which they're transition metals. So they easily lend and take electrons from other molecules. And just to be brief, a catalyst is a chemical substance that increases the rate of a reaction but doesn't change the thermodynamics of it. And if we wanted to, we could also test for different colors, which have different wavelengths, since we only tested pH. And we could have also used a different dye. So instead of using something like beet juice or raspberry juice, we could have used cabbage juice, because it changes color drastically based on pH level. So if we wanted to test color, that would have been a good alternative. And finally, we could have done different tests for smaller ranges of pH. So we use increments of 0.5 from 4.7 to 6.2. So we could have done something on a much smaller scale from like 6.15 to 6.25. Okay, thank you for listening. Any questions?
Nice experiment. One quick question about your projector, that chart. There's only one pH that pushed the. So how are you sure those two are not outliers?
Do you mean the two with the numbers?
pH 6.2. I know the other chart is more showing you the trending is going up, up, up. And this one is like staying low for the projector, and all of a sudden there's one jump. I figure it might be better if you add 2 more data points, left and right, to show the trend. to confirm it's not an outlier going up instead of going down at 6.2.
Yes, because yeah, that would be one of our further experiments. If you so one of our further experiment is testing whether higher or lower pH, and yeah, I agree with what you were saying, because yeah, you can add like another data point on both sides and make the pH range a little bit bigger, and we just chose this range because it's easier for us to like control it, because initially we wanted to like calculate how much we needed, but that's like pretty much impossible. So we just like decided to drop, which is like way easier and more efficient. But like that means we kind of had to like limit our pH range. But if we have more time and if we had access to like better, or not better, but like we have access to more equipments, we can probably test probably even more than one data points on both sides, and that would be really helpful for our data.
So if the 6.2 pH was the optimal range or the optimal pH, do you have any like scientific reasoning behind why you think that is the case?
Well, it's not so much as reasoning, more than like educated guess. But we were researching, and then like we didn't think of much of like the acid and the base, and and the results sheet also shows why we think so. But then another like reasoning could be that maybe the acid or the base like it altered chemical structures like inside the cell, which could be an issue. And yeah,
So there's different theories that they have online too. So they found similar results, and the problem is, it's just the main part is the middle part is usually the optimal pH, and if it gets too acidic or too basic, that poses kind of a problem. And this data specifically applies to just simply beet juice, because it has a different amount of anthocyanin. The ones online did like raspberry juice or different juices that have anthocyanin but a different concentration of it. So our theory is backed up by research, of course, but it's specific to beet juice. Yeah.
Thank you.
So I know you had it as a future thing to look at, but I'm curious about the possible lifespan of cells that you could make from this, since it is plant-based and could degrade fairly quickly. So what's your thoughts initially, without having done the experiment, on the durability and need to refresh this? And again, thinking about real-world applications, like if you were trying to coat, you mentioned windows on buildings or something like that, how often do you think that you would have to refresh it, or what would you do to increase the lifespan of it?
Wait, so do you mean like an initial consideration when it's compared to like other solar cells, or it's just like?
Well, just because, do you have any thoughts about what the lifespan of some of these might be, because it's plant-based? And then what do you think you could do to extend the lifespan of it?
So this experiment was kind of to add on to that point. We were trying to increase the efficiency of our solar cell. And so there's many different aspects you can change to increase our efficiency. We simply just altered the pH of the dye, just the dye specifically. But you can alter every single aspect that we had in the other diagram. Like the TiO2, you could possibly use something else. And so the main thing about these solar cells is that they're cheap. So even if you have to refresh it, it would be very cheap. So, yeah.
So when you made so can you go back to your data where you have your the one with the highest current? So for solar cells, two things that affect how much current can be generated. One is area and the other one is intensity. So how do we know that that highest current that you got there wasn't because you maybe made a bigger solar cell, slightly bigger, and maybe you didn't control the amount of intensity of light on the solar cell? Like, how do we know it wasn't one of those geometric factors versus actually what you're claiming, which is the pH?
So for each of our trials, we use the same amount of like electrode glass with the same surface area, so that was constant. And also for the projector and the flashlight, we always put the electrode glass right, like we put it pretty much on the flashlight or projector.
Any other questions? And if not, let's thank our group.
We didn't get screwed.
All right, collagen board.
Hi everyone. So today we will be presenting magnetic biopolymers. My name is Bhagya.
My name is Danny.
My name is Martin.
My name is Angela.
And my name is Kaylee.
So before our in this experiment, we'll mainly use three kinds of materials. So let me introduce to it. The first one is biopolymers. So if I want to speak about biopolymers, so I need to introduce polymers first. So what is polymer? Poly means many. So polymer is a kind of substance that made up of large quantity of repeating units. So we call these repeating units monomers. Then what is biopolymer? Biopolymer has two additional characteristics upon the polymers, which is they are produced by biological systems and they're biodegradable. So as we can see, and from the picture is DNA. So DNA is a biopolymer and is made up of nucleotide monomer, so which has 4 base pair ATCG. And the next one is ferrofluid. Ferrofluid is a kind of nanoparticles which is magnetic that's suspended in water, so which makes it have magnetism. And the last one is gel. The gel is solid jelly-like material, and it is kind of substantially dilute crosslink system. So let's take an example. I'll take sodium polyalkylate as an example. It often appears in diapers. So we all know that sodium polyalkylate absorbs water. So how does it absorb water to forms a gel? It is because when it dissolves into water, and the sodium ions will dissipate and will come out from the polyalkylate. And at this time, there will only be negative ions in it. And because they have the same charges and they will repel each other and they extend to form like a network structure. And this will cause osmotic pressure. So the water will come in it, which makes it absorbs more water to form a gel.
So moving on to why magnetic biopolymers in specific. So biopolymers can be mixed with its cross-linking agent, so it can form a gel that way. So we can insert a ferrofluid magnet, as Danny explained, into the gel to give it magnetic properties. So the magnetic field will basically remain in wherever we're injecting the gel to apply to, and it will have a magnetic field that will keep it in place. So basically the magnetic field in the gel will keep it so that it doesn't move while it's applied to whatever application you would like it to go into. And throughout our research, we focused on something called osteoarthritis, which I will explain later, but it is we're basically trying to improve the weakened bone with more collagen, which is a protein, and has shock absorbent features, which the ferrofluid magnet provides it with. And we will also be going into various applications that magnetic biopolymers are also used in. So our objective is to create a magnetic biopolymer that has a gel consistency, so it will have a balance between solid and liquid, so it's still movable, and to have an active magnetic field, so it still has the magnetic properties given by the ferrofluids, and it would be used to relieve joint pain. So going into the medicinal applications, osteoarthritis is one of the main things that we wanted to focus on, and this is a common form of arthritis that is affected by millions of people worldwide, and it occurs when the protective cartilage that covers the ends of your bones wears down over time. And two other diseases and syndromes that are also related to this includes patellofemoral syndrome, and that's when it contains the disease describes the pain in which the front of the knee is like corroded by the bone weakens in front of the knee, and also known as a patella. And the last one is fibromyalgia, which is a disorder characterized by the widespread of musculoskeletal pain.
So some other medicinal applications using magnetic gel could be to release drugs by using the strength from the magnetic field. Another possibility could be to unclog arteries using the magnetic gel. And although there are not many applications for the magnetic gel in besides the medical field, it could be possibly used to prevent metals into the food or the removal of pesticides. And since magnetic particles do not interact well with sound waves, the magnetic gel could be used to create a noise-canceling earplug, which could be turned on and off in the presence of a magnetic field.
The biopolymers we used in this lab are iodocarrageenan, gelatin, and collagen. Iodocarrageenan is a polysaccharide polymer that comes from red algae. It has monomers of galactose and anhydrogalactose. It forms a structure by forming bonds of calcium ions, and the calcium ions bond with the sulfate groups. We also use gelatin, which is a protein biopolymer. Protein is divided by collagen and is prepared by the thermal denaturation of collagen. It forms a structure of hydrogen bonds. We also use collagen, which is the protein found in bones. It is a component of cartilage.
So focusing on the application of osteoarthritis, the arthritis that we wanted to focus on was in the joint, so that has cartilage that's affected, and cartilage is mostly consisted of collagen, which is a protein that promotes self-proliferation, and cartilage is a tough and flexible tissue, and it's also shock absorbance, which is why the ferrofluid magnets have a property that has shock absorbance as well. And basically, we wanted to enhance the bone functionality within the affected area, so the gel would provide the shock absorbance with correlating with the ferrofluid magnet as well. And this serves as an alternative for implants because implants have a background of causing infection. So this is a positive alternative for that.
To create our ferrofluid, we needed to create nanoparticles. Usually for microparticles that have multiple domains. Domains are areas where the magnetic field of atoms align with each other. But as you go smaller into nanoparticles, eventually there's only one domain, which results in superparamagnetism. This makes them very responding to a magnetic field. We also use magnetic nanoparticles also make the substance they're in magnetic, and we had to alter our nanoparticles to be compatible with water. We use 3-mercaptopropanoic acid, and this is a capping ligand we use to cover the nanoparticle, and this is a polar tail, which is able to be suspended in water.
So after doing all of our research, we decided that our overarching question for our project would be which mixture of biopolymer and ferrofluid can create a magnetic and movable gel. And our original hypothesis was that if 2 milliliters of ferrofluids, if we mix 2 milliliters of ferrofluids into 25% collagen, then a magnetic gel will be created, which can later be injected into a pain to decrease into the joint.
So the first part of our procedures was to find the appropriate gel consistency. So we created gels with different concentrations of collagen, iota-carrageenan, and gelatin. And we measured the Young's modulus for these, which is basically the elasticity or the resistance to compression. And we did that by stacking pennies on these gels. And so we basically wanted to find a biopolymer gel that is movable, so we want a balance between a liquid and a gel consistency.
The next part, we have to make our ferrofluid solution. We use ferric and ferrous chloride as our iron sources and ammonium hydroxide as our oxygen source to make iron oxide. And then we use 3 mercaptopropionic acid to cap it off to stop it from growing further. We mix about 1 milliliter of each solution to biopolymer gels.
So next, we tested whether the ferrofluid works in our gels. So we first measured the Young's modulus for each gel we made, and then we recorded data and plot a graph. After that, we tested the application specific, which we put in magnet, placed our ferrogel onto glass slide and move it with a magnet to see whether the ferrofluid works in our gel.
So putting this into a context of osteoarthritis, so someone would inject this gel into the joint or the location that it would be necessary in, and it would basically, we would use another magnet to move it around to fit the person's knee or joint. So that's where we wanted to test the movability with a magnet.
So we mentioned Young's modulus several times before. So let me introduce what is Young's modulus. So basically, Young's modulus is also called elasticity modulus. So it basically measures the elasticity and the stiffness of a substance. So the principle of Young's modulus is basically because when a force exerted on an object, it will cause deformation. So a more elastic object is, so more deformation it has. So Young's modulus basically focuses on a relationship between the stress and the strain, these two kind of things. So it has an equation, which is the force exerted multiplied by the original length divided by the product of the contact area and the increasing length. So, but that's a general equation of Young's modulus. So we made a more specific equation for our experiment, which is so we use this equation to do some specific calculation in our experiment, which is the number of pennies and multiplied by the mass of each penny and the gravity constant, also multiplied by the thickness of gel divided by the volume of the penny to calculate the Young's modulus for each gel we made.
First, we chose collagen as our first biopolymer because collagen is the most commonly found protein in bones. In addition, collagen helps cell proliferation and helps bind to other proteins. However, through our experiment, our collagen gels would not be able to turn into gel consistency, so we decided to use other biopolymers such as iota-carrageenan and gelatin, which is a derivative of collagen. So here are pictures of our collagen gels. In the upper right-hand corner, that is our 20% collagen gel. And next we made our 25% collagen gel. And then finally we decided to spike up our collagen by making a 50% collagen in order to try to make a gel, which still did not work in the end.
So moving on to the second biopolymer that we tested the one that we did previously last week, which was iota-carrageenan reacting with the calcium chloride. So calcium chloride is actually the cross-linking agent for iota-carrageenan, and we did 4 types of concentrations for the calcium chloride. So basically, we would have a constant for the iota-carrageenan, which was 1%, and then we had a variation of the CaCl2 concentration. So we would heat up the entire solution and then we would cool it, and that's how the gel would be created. So we had 3 variables for the concentrations that we had. So first was just ferrofluid. So we did that for every concentration of CaCl2. And then we just had one with 25% of collagen. And then we had one where combined both of them. And highlighted, you could see the ones that we found most ideal, which had the balance between the solid and liquid state of matter, and it had slight magnetism. So as you can see here, these are all of our gels for iota-carrageenan and CaCl2, and here are the ones. This is the 0.25% of CaCl2, and this is the 0.3% of CaCl2, which we found most ideal.
As we tested our Young's modulus, we found the more CaCl2 we put in the gel, the higher the Young's modulus was.
So our third biopolymer is gelatin. So we made gelatin gels with 30% and 50% concentrations of gelatin, and we also added 1 milliliter of ferrofluid as well as collagen into the gels. And as you can see, all of our gelatin gels came out really stiff, and even the ones with ferrofluids in it were very slightly magnetic, so it wasn't as magnetic as we had hoped. So here are pictures of our gelatin gels. Those are 50% and 30% gelatin. And as you might be able to see, they're really stiff and really dry. So that wasn't the consistency that we were looking for. So far, our gels haven't really been magnetic either. So, well, they have been, but not as much as we had hoped. So we decided to make 5% gelatin gels, and we just wanted to test the impact of the ferrofluids on those gels. So we added 0 drops, 15 drops, and 30 drops of ferrofluid into those gels. And even in the 30-drop gel solution, it was slightly magnetic, and it wasn't really movable. So we wanted to make it more magnetic.
When we tested the Young's modulus, we found that the 50% was very high, and this is the reason why it was so stiff.
So at this point, we haven't really got a magnetic gel, so we decided that we would just take one gel that was not too stiff but not too liquidy, and we would just spike it with a whole bunch of ferrofluids. So in our 0.1% CaCl2 and 1% iota-carrageenan gel, we added around 2 milliliters of magnetic nanoparticles, and that made the gel extremely magnetic and movable.
As you see, it responds to the magnetic field, like we hope.
So in conclusion, as we saw through the graphs, the Young's modulus increases as the CaCl2 concentration increases as well, and gelatin, because as we added more of the concentration of the actual biopolymer, it added more of the liquid and solid substance that we were looking for and hoping to receive. And it was directly proportional, so as both of them increased, it both increased at the same time, so it was directly proportional. And this is until it reaches the maximum point of gel stiffness before it reverses the reaction and becomes a liquid once again. And the lower the Young's modulus, the more movable it was. So as you can all expect, a liquid is more movable than a solid. But we were trying to find the balance between a liquid and solid, which is why the younger the Young's modulus, the more movable it would be. And the higher the concentration of ferrofluids, the more magnetism it had, which is also kind of a given because the more magnets that you add, the more magnetic the field would be. And the elasticity of cartilage we found was 7.79 MPa for normal cartilage and 1.36 MPa for arthritis. So that's just like a comparison to what we actually found.
So after this experiment, we also came up with several refinements. The first is we noticed that the binding ligand we use is 3-mercaptopropionic acid, which is toxic and will do harm for human bodies. So since this kind of gel will be injected into human bodies, so we cannot use this, we can either make it non-toxic or we switch to another polar ligand. The second is we also should control the amount of ferrofluid in the kind of gel, because also it should be injected into human bodies, so we should control the amount of ferrofluids in it. So that's all. Thank you.
Very nicely done. Quick question about the magnetic stuff inside the body. Are you concerned about the use of MRIs?
Yeah, so multiple questions have arisen as like a magnet and you're walking through airport security and it beeps. So what we found was just the doctor that's taking, or like the physician that's taking the MRI would be aware of the magnet that's in the body, and this is something that we'd still have to further research, but they would probably be aware of the magnet that's in the body, so that would yeah.
All right, I have a question. So you did mention at the end the modulus for cartilage, or the elasticity for cartilage. So how does that actually compare to the data that you got, and how would you further refine your material to match what it is you're looking for this application of cartilage in the knee?
So our experiment, we also calculated the Young's modulus for our experiment. So we can see that the normal elasticity of cartilage is 7.79 Pascal for normal. So we need to switch to make our gels which has a similar Young's modulus for that. So from our experiment, I see the iota carrageenan with with concentration of calcium chloride with 0.3% would be the most near the Young's modulus for cartilage.
And to further reiterate, so cartilage is mostly composed of collagen, which is not the protein that we tested and got our the data from this graph from. This was from iota carrageenan and CaCl2. So with the cartilage, it would be consisted of the collagen biopolymer and not this one.
Yeah, because so for that data, you're at like kilopascals, I think?
Yeah.
Right?
Yeah, MPa. So it's megapascal.
Well, so I think that looks like kilopascals. Megapascals would be like 10 to the 6th. So it's actually like quite an order, like a few orders of magnitude higher of a modulus. So there'd probably be some sort of work you'd have to do to like figure out how to get it to really match cartilage if that's the application you are going for. But that might conflict with the sort of movability of the gel, right? Because if it's super, super stiff, that might be challenging. So can you think of some type of way of getting around that sort of conflicting problem of you need a stiffer gel, but you also want it to be a movable gel?
There's actually an application where one of the instructors actually told me about. So there's like a paper that consists like a prescription, like a drug inside of it. So when the magnetic field is attracted to it, when it's injected into the human body, it'll like release the medicine into the body. So with the magnetic field, it has that property of doing that. So maybe for further research, we could find out something that when the magnetic field is present, the gel could become stiffer in a sense, and when it's not, then it would be more movable.
Or thinking maybe of some way of like cross-linking it once it's inserted and it's already sort of in place, as opposed to having it already like pre-made or something like that. Other questions?
Hi. Have you guys seen any research on the general biocompatibility of the ferrofluid itself?
Yes, we have researched that some amounts are non-toxic, which we would have to also further research. But the amount is uncertain.
Okay, thank you.
All right, if there's no other questions, then let's thank our group. Nicely done. All right, so group 8. H2O. Just add water. That is their full name.
Hello and good afternoon. My name is Mustafa.
I'm Riley.
I'm Jackie.
I'm Arjun. And I'm Majid.
And we'll be discussing filtration of different solute impurities using graphene oxide. So just a quick background about the current state of filtration. Over 780 million people globally go without access to clean water. And because of this, 3.4 million people die every year due to water-related diseases. So there are 3 common filtration methods used to combat this, which is chlorination, solar water disinfection, and biosand water filters. Chlorination actually has health detriments in the long run, and it does leave an odor and a taste. Solar water disinfection takes 6 hours to just produce 1 batch of clean water, and biosand water filters have a relatively short lifespan of 1 year, and they're pretty bulky too. So we will be using graphene oxide to construct our filters. So why did we choose it? Graphene oxide has a lot of unique properties. It has a charged oxide layer, which allows it to perform electrostatic interactions and can be used in desalination. And it contains pores on the nanoscale as well. So it has pores that range from 2 to 15 nanometers, which is extremely, extremely tiny. And this proves to be really good for filtration. And it's also really chemically and mechanically stable, so it'll have a longer lifespan as well.
So our research question was, can graphene oxide nanostructures be used to filter out solute impurities in water? And using this research question, we formed a hypothesis, and it was that geo nanofilters will potentially remove impurities with greater efficiency than traditional filtration methods. And so we began by using a nylon filter, and we tried trapping a graphene oxide solution on the filter, so coating it over it, but that didn't work, and the filter got clogged. So we tried to dilute the solution with water, and then we coated it again, but the nylon filter still clogged. And then we also tried to use a sonicator to dilute it even more, but again, it got clogged.
So the next day, we decided to switch up our experimental design by instead just baking another layer on top to see if it would scrape off in a more efficient manner or just at all. But unfortunately, it did not. So then the following day, we decided to use pre-made coffee filters and cut them to be the same size as the filter we were going to be using. And then we put different amounts of drops of our graphene oxide solutions on the filters until we decided that it was like saturated enough. And so we put those in the oven, baked off the water, and then we were left with a dried graphene oxide membrane. So this was our experimental setup. As you can see, we had our dried membranes on the left, and then the middle picture is them inside of the filter that we pieced back together with the binder clips, and then we just used the syringe with the solutions as normal.
So the solutions that we used to test the filters were salt water, a bacterial solution, an iron chloride solution, and finally an oil and water mixture.
So going into the experiment, we had expected that we would be able to partially remove the salt ions because we weren't sure how well they would interact electrostatically with our graphene oxide filters. We also thought that we'd be able to clear out the bacteria because we were pretty certain that they'd be big enough to get caught in the filter, and that we could partially filter the iron solution. Again, unsure about how the ions would interact electrostatically, but we did think we could remove all the oil.
Okay, so for the saltwater solution, we made a really concentrated solution, and we originally planned on using a salinity meter to test the amount of salt in the original solution, and then after we put it through the filter, but we didn't end up getting one of those. So instead, we just reacted it with silver, and as you see here, there's a white precipitate, so there was a reaction, meaning there was still salt in the solution, but we were unable to test the original concentrated solution, so we don't know if there was more salt there and we actually ended up filtering out some of the salt, or that we just didn't remove any of the salt.
So the next solution that we decided to filter was the bacteria, and in this one we just used a visual analysis to see how successful we were. And you can see that's the original solution there with some bacteria mixed in, and that's the after we pushed it through our filter. So it's significantly less murky. And just to prove that it wasn't the coffee filter and it was our membrane that was working, we also pushed it through just the coffee filter, and you can see there's very little difference. So this just kind of proves that on a smaller scale, graphene is more reliable than the current uses for filtering bacteria.
Okay, so we also, for our iron solution, we thought that we would be able to filter out some of the iron with our filter, but we were wrong. As you can see over there, the solutions look identical, so we didn't filter out any of the iron. And in the middle picture, we used a zeolite for a different copper lab that we performed last week, and it cleared out the copper, so we know that it is possible to filter it, but the graphene oxide did not work.
And so the last solution that we decided to filter was actually a mixture of canola oil and water. And so what we did was we took off the top of the filter and put drops of oil in, 25 milliliters. And actually only 1 milliliter got through to the final solution. So that means 96% of it was removed. And you can see that's actually more effective than the two current methods. So yeah, it's better for removing oil than predatory microbes.
So, if we could change something with the experiment that we've done, we would try sealing our filter better. Since we did crack open a filter and put in our own, it wasn't sealed around the edges, so the solutions would leak out of the sides. And also, we had no control over the size of the graphene oxide pores, so we didn't know exactly what it would do. And we could also analyze the structure of our graphene oxide membrane to see what exactly the properties it holds.
Okay, just for an overview, we used the graphene oxide filter to try to filter out 4 different solutions because it's typically used just to filter salt out of water. So we wanted to see if the idea of using the membrane could filter out other contaminants. And we really found out that pore size affects the ability of the filter to get rid of contaminants. And we learned that it can filter bacteria. And it has such small pores that we thought the bacteria would get stuck, and we were right. And with the a pure graphene oxide solution, it's possible to remove all ions, but with our diluted solution, some of the ions were still removed. In the future, if someone was planning on building off of our research, or if we could continue to work on this for more time, we probably would use a pure solution just to see that if it made a difference in how well it filtered, and try to use an electron scanning microscope, which you can see on the nanoscale, not the microscale, because since it has nanopores, we wouldn't be able to see all the pores if we just used a regular microscope. We would also try maybe resynthesizing using a different method, so we could maybe adjust the pore size to see how much of a difference it would make in filtering out other contaminants.
So why does this matter? Well, there's actually a lot of real-world applications for filtration, obviously. Some of them are listed here. Iron is a huge contaminator in well water and underprivileged areas. Saltwater deposits can sometimes sneak up and infect fresh water, leading to illness. Oil spills are obviously huge issues with fishing. And the most important one to us was bacteria, since I've personally seen a lot of people get illnesses from contaminated water abroad. So we'd say that was the most important one to filter out. The practice of ion sponging, which is where the electrostatic interactions pull some of the ions out of the solution, is something that's unique to graphene oxide, so that could be the next big step towards clean water. Thank you.
Thank you.
Considering that your main application or one of the main application was bacteria removal, did you study the size of the bacteria or the type of the bacteria that you tested?
So actually, bacteria or all bacteria are around, they're micro-sized, so they're not nano-sized. They're around, they differ in size, but they're all micro-sized. So our filter was more on the nanoscale. And so the pores were too small for the bacteria to go through. So in a sense, yeah, we did study them and we did study their size and we figured out why they didn't pass through.
And if you're looking for the specific details about the bacteria, it was called Lactobacillus rhamnosus, and it was 200 billion CFU, or sorry, million.
So, what was your hypothesis for the iron not not being filtered out? One question, and second was, did you try a concoction, all four of them together, and see what happens? Just curious.
So we didn't actually try a concoction because we wanted to try them separately. But for the reasons why the iron wasn't filtered, we did hypothesize multiple reasons. So if you can go to the slide, the iron, yeah. So we speculated that maybe the pore sizes were too big, and so that allowed the iron ions to actually pass through the pore size. Like if it was too big, it's just going to pass through. We also speculated that maybe there wasn't enough electrostatic interaction between the graphene oxide and the iron itself. And finally, we also speculate that it might have been something to do with our membrane integrity when we synthesize the GO.
So based on what you learned through this experiment, like the gentleman asked, if you mixed everything, what I want to know is there a universal way, like basically, is there one grand filter that can filter everything out?
Oh. No. Since all different types of contaminants have a lot of different traits, you can't just use one filter to filter out all of them. As seen just on this slide, you can see that we couldn't get our membrane to filter out the iron, but a zeolite did work, and activated carbon or activated charcoal is another way to filter out contaminants, but none of them work for all different types because they all have different properties that attract to different contaminants.
Okay, so my second question, real quick, is your iron didn't work. So can you explain why your geo filtered versus something like, I don't know, like a Brita filter that can filter out heavy metals? How does yours, not that it doesn't compare, but why is it that the Brita filter ones can filter out some heavier metals and yours cannot? Like what's different, chemically speaking?
So the Brita filters are much more like commercialized and like mass produced, so they have a lot of uniformity like across all their filters, which is something that like we couldn't replicate in a lab using like a pipette basically. Also, I'm unsure about the Brita filter's actual structure and why it's able, like what its pore size is, like and how it stacks up to ours, but I do. Okay, so the Brita filter, I don't know if it has any sort of like electrostatic charge to it or what kind of chemicals they're using to filter it, but ours, because it's graphene oxide, has a very like specific kind of like electrostatic energy, that so it can only react and like trap certain things. Yeah.
So the question I have for you guys is, you mentioned the pore size is too big. How would you guys control for pore size?
So using the method that we used, we couldn't like at all. There are different methods out there, like using like different gases that like punch holes through like a certain diameter or whatever. But the way that we did it, there's no way that we could have done it. So I mean,
Yeah, so the way you guys did it, so what would be another way that you guys could do it that would control for pore size?
Well, we originally were going to use the sonicator, which we had, and we listed that it didn't actually end up breaking it up enough, but it does break up the sheet so that it would create different size pores, and depending on how long you would actually use it for would depend on how big the pores got and how broken up the graphene oxide sheet would be.
And another thing that affects the filtration is not just the pore size, but the number of layers, right? So graphene oxide is so thin that the layering is it's staggered so that even if it gets through one layer of the pores, it'll still be caught in the next one because it's staggered like that. But we had such a thin layer and such a diluted concentration that really didn't work as well with this solution.
Thank you.
It's a simple question. On bacteria, you mentioned that you used basically you used what you saw, you used visual distinction, just see before and after. Why didn't you use anything else? Why did you just use visual?
Okay, so we did actually try and use an agar plate to take a couple drops of the bacteria solution like before it's filtered and put it on one side, and then take our filtered bacteria solution that looks much more clear and put it on the other side. But unfortunately, we did not see any results on that agar plate after leaving it for 24, maybe 36 hours. But that could largely be due to the environmental conditions that it was in the lab and improper time given to grow.
All right, nice job. Thank you. All right, last but not least, metal oxide, group 9.
Good afternoon. I'm Alex Beloyu.
I'm Aaliyah Raven.
I'm Mackenzie Tassiello.
I'm Hanson Liu.
And I'm Vincent Silva.
So the experiment we conducted is regarding the effect of different construction methods of metal oxides on efficiency of dye-sensitized solar cells. So what is currently happening in the community regarding these solar cells? So currently, scientists are looking to improve solar cells in the aspects of efficiency, practicality, and cost, as currently they have many problems. So currently, scientists have been looking into advancements in solar batteries, such as developing molten salt batteries and graphene batteries, creating more wearable solar cells to be used in electronics and watches, and also creating transparent solar cells.
So why should we care? Well, as you can see in this chart, in recent years, global temperature has been on the rise and it's hit its all-time peak. So the need to switch to renewable energy is more prevalent than ever. So our question that we're trying to answer is how to make an efficient solar cell without silicon. Because the problem with silicon is that it's expensive to fabricate, so the average households cannot afford it. Only around 9% of all households in California even have solar panels, and this needs to change. Dye-sensitized solar cells, like the ones we created, are inexpensive, but they're less efficient. So this research will test many different possible solutions to find which solar cell has the highest electrical output.
So this is a diagram of our solar cell that we constructed in our lab. So on the white layer here and the white layer here is our glass slides, and there's a thin layer of fluorine-doped tin oxide on top, which serves as the conductive layer. And right over that, over here, is the graphite catalyst, which serves as, it lowers the activation energy for the redox reaction of the iodide electrolyte. And then underneath that is the anthocyanine dye, which underneath that is the metal oxide, which is the semiconductor. And the way the electrons flow is the light passes through the dye and excites an electron, which moves onto the metal oxides through the conductive layer and then goes back through the circuit. Meanwhile, the iodine is undergoing a redox reaction, which allows the electrons to be replaced in the dye that were through the circuit.
Okay, so our experiment primarily focused on metal oxides, and the purpose of these metal oxides, or the prime purpose, is that it applies a nanoparticle-sized layer over our solar cell, and what that does is it allows for increased absorption, and increased absorption logically results in more electrons being in the circuit and a higher electrical output due to the fact that metal oxides are an integrated layer that trap and transport the photogenerated electrons.
So in our experiment, we tested several different metal oxides, the first being titanium dioxide, also known as TiO2, and it's commonly used in dye-sensitized solar cells. Its large current density, exceptional stability, and low cost make it an ideal material. And the next metal oxide that we tested was magnesium oxide. And magnesium oxide is slightly insulative, which gives it some different properties. It also has a nanopore structure, which increases dye adsorption. And so our last material is zinc oxide. And zinc oxide also has a large surface area like the other metal oxides, as well as a reduced recombination rate, which means more electrons can successfully flow through the circuit. It also has direct electron pathways, which increases the efficiency of the solar cell. So our research question was basically which construction of the metal oxides will produce a higher voltage output on the multimeter. And so we predicted that a solar cell constructed by pre-mixing the MgO and the TiO2 would significantly increase the surface area due to a nanoporous complex that it would form, and this would increase voltage output.
All right, so step one of our experiment, we had to prepare the metal oxide nanoparticles. So we're given the 3 metal oxides in a powder form, and then we measure out 2 grams of them, and then we add acetic acid, which basically turns it into a solution so we can use it to layer it over the solar cell, and we just grind for 15 minutes. After the 15 minutes, we add a drop of Trident X, which similar to the ferrofluids in the oleic acid, it acts as a capping ligand. And what that does, it prevents the nanoparticles from combining and aggregating to become a larger complex, so that they can do what nanoparticles do, increase surface area and all that. And we continue grinding. And then we layer the solution over our solar cell, which was way harder than it should have been for us. And then we ended up, after we're done, we heat it and cool it so that the solution can dry on the solar cell. During that time, we prepare our dye, and we basically take frozen raspberries and we filter it so that only the juice is left. And we use raspberry dye because we want to absorb the blue light, because that's the lower wavelengths and a higher frequency, which means there will be more energy and possibly more electrical output.
Yeah, for step 4, we took the second slide that hasn't been used yet, and we coated it with a graphite layer, which is used in order to act as a catalyst to lower the activation energy for the iodide redox reaction. And then in step 5, this is where we assembled our solar cell by placing the 2 plates together and clipping them with binder clips in order to connect the electrodes. And here we added iodine, which acted as the electrolyte for our solar cell, which helped the charge transfer process, where as light was converted to electricity by the dye, it lost an electron and acquired a positive charge, which here the electrolyte then worked to basically replenish the dye and regenerate it. And then for the last step, we tested our solar cell by placing it on a projector, and then we used a multimeter in order to get the millivolts and microamps of that the solar cell was producing.
So after recording our data with the multimeter, you can see that the TiO2 with the MgO layer is significantly higher. It has a higher voltage output, and it's almost twice of the control, which is the TiO2. Also, you can see that the TiO2 with the ZNO layer is slightly lower in voltage output than the TiO2 by itself. And there's basically the same trend for the current, and yeah, the TiO2 with the MgO layer is much higher than the other 2. And also the pre-mixed, the 2 pre-mixed have little to no current and voltage. So then using the voltage and the current, we calculated power. And as you can see, the TiO2 with the MgO is much higher, and the zinc layer is slightly lower. And so we believe that the reason why the zinc layer had a lower output was because it was zinc ions would form on the zinc layer, and this would hurt the electron injection, which is basically the emission of electrons from one solid into another, and this would decrease the overall efficiency of the solar cell.
So you might be wondering why MgO yielded the best results. Well, think of it like a ladder effect. Because there are 2 layers of the metal oxides, the second layer assists the electrons to go to the excited state. So pretty much the excited state is when the electrons are able to go through the circuit. So if MgO is assisting it, then they could go there with less energy. They go from the valence orbital to the conductive orbital and pass through the band gap. It's better to have a smaller band gap because it requires less energy to pass through. Because MgO has a larger band gap and TiO2 has a smaller band gap, they average out. Also, another reason that MgO yielded the best results is that the thin layer of MgO on the TiO2 acts as a barrier for charge recombination. And that's pretty much the time it takes for the electrons to fall back down from the excited state, and that's not what we want in a solar cell because we want all of the electrons to go through the circuit. So if the MgO is a barrier, then it helps solve that recombination problem. And also, the MgO creates nanoporous complex when it's paired with the TiO2, and that's a picture of a nanoporous complex right there. So as you can see, there's more surface area for the dye to cover and more pores for it to go to. So there's more light is able to be absorbed by it.
So the main reason why we think that the mixtures didn't work and that the layers yielded a very much higher result is due to aggregation. So basically, with the metal oxides on their own, they're in their nanoparticle state and size, which gives them their large surface area property. And then when you mix the two together, it's very possible that they clump together, which is aggregation. And when you aggregate, there's a loss of the nanoparticles, so now they're in the micro level, and there's less surface area due to that. And with less surface area, less dye is absorbed, and then less electrons go through the circuit.
So in conclusion, a solar cell that is layered with TiO2 and a layer of MgO enhances energy conversion efficiency. Now this is what we tested in our research, but Aaliyah is going to tell us some additional experiments that we could further our studies.
So due to the fact that we believe that the recombination rate is the biggest factor in why the MgO is the success, so we want to test the recombination rate with photoluminescent spectroscopy so we can quantify the amount in comparison to the other metal oxides. And next, we believe that also like a human error in our experiment was the production of the nanoparticles, because some nanoparticles when we produced had a more bubbly solution than the others when mixed with the acetic acid. So we wanted to test different ways to make these nanoparticles and see if that affected the output of the current in the solar cell. And lastly, we want to test if layering the metal oxides makes a difference, for example, like with the band gap, and if having the TiO2 on top of the MgO would reduce the reduction rate.
Thank you.
Does anybody have any questions?
Hi. So sorry if I missed this, but so you tried TiO2 by itself as kind of your baseline. Why wouldn't it work if you just had a layer of MgO or a layer of zinc oxide on its own? Why did you have to mix those?
So there's been a lot of recent studies lately that layering them on top of each other work better, and the structure of MgO does not work as well by itself, and it needs a supplement metal oxide. So rather than testing, we also did not have enough time to test all of them. So rather than testing just MgO and just CNO, we decided to test both to see which layer would work better.
Thanks.
We did a good job.
Yes. I agree. Hi, Zach.
How's it going, guys? So you guys use glass with a thin conductive layer for your solar cell. How come you guys don't use something else that maybe conducts better, like copper or something traditionally used in a wire? Why do you use glass?
Oh, we use glass, sorry, because we need a clear structure for the light to pass through, because if the light isn't passing through, then the electrons in the dye aren't getting excited, and then the solar cell just won't work.
Very good.
All right. We don't have any other questions. Thank you.
Let's go.
before we all get to go outside and conclude and have a nice reception with some food and drink, because I'm sure we're all very hungry by now, I just wanted to have us all acknowledge two very important groups of people. One, our amazing instructors who really facilitated all of this learning this week, so thank you guys so much. And number two, to the students who all did a really, really excellent job. I've done this program for multiple years now, and every year I'm always impressed, especially going from the beginning of the week when we're just hearing these nascent proposals to the final presentations. It's always really, really impressive how you guys pull all of this work together. So you guys did a really, really excellent job. So congratulations to everyone. So now we can all go out and enjoy some food and beverages. So thank you very much.